Hello, sir. Sound is not correct. It is disconnecting. So, sir, still it's not okay for me. Yeah. It's not.
Yes. Hello. Is it coming properly now? Hello?
Yes, sir. Yes. Now, okay.
Oh, okay. Okay, good.
Alright.
Okay. So let me share my screen and let me will go with the stuff that we have left in the last lecture. Okay. So I think international students, sir has started with the transistor basic. Is it right? Is it true? Sir has covered the transistor basic in other class. Yes or no? Sunil sir has, I think, covered. Yeah, Ajoy. Yeah. Okay. So let me start with a little bit of revision on that, and then we will start with the actual stuff that actually we are going to be discuss on this lecture. Okay, and depend upon that lecture, you have a task number 9 and task number 10 is there, or we can say session 9 and session 10 is going to be there. Okay, so what is the basic task we have? Like we need to identify a different configuration of the transistor. Okay, but before going to understand a different configuration of the transistor, first we need to be sure with that what is a transistor, what are the basic condition under the biased and under the non-biased conditions. Okay, so in the last lecture, I think you have gone with the stuff of the transistor basic. Like there are NPN, PNP type of the transistor, how transistor going to be formed, how it is going to be articulate, what are the area, how this depletion layer has been created. This all stuff I think you have seen in the last lecture. Okay, we need to start from this particular diagram. Like when we are considering that our transistor is not applied, we have not applied anything to our transistor. Okay, so that is considered as an unbiased transistor. Unbiased, it means there are no power supply in any terminal. If such type of the conditions are there, and during that situation, what are the we can say depletion region, what are the type of the current flow is possible on your transistor, if we can look their characteristics, so that we can say that is a condition under the unbiased transistor condition. So if you are not applying any power supply to any terminal, then what happens by default, there are between base and emitter, take a laser pointer, yeah. So between base emitter junction, okay, over here is N is there and P is there, so depletion region has been created. Okay, a similar type of the stuff or similar type of the things that you have observed in your diode characteristic. So under the no biasing condition of the diode, it will create a depletion region over there between P and N junction. Okay. Similarly, this side also it is forming the PN junction under the collector bias junction, so it is also creating a depletion layer over here. So we can say base is a lightly doped. Like as per the doping characteristic, we have seen that base is going to be lightly doped. So the length of depletion layer is little bit higher as compared to the emitter and collector. Okay, so that is the stuff is going to be there. And why there is a size is higher? Because there are less free electron, free charge carrier are there, and due to that, the depletion layer is going to be expand on that particular medium. Okay, so this is a thing like actually going to be happen when you're not applying anything any power supply, and if that transistor is just as open, so such type of the junction condition, or we can say that depletion region condition is already there. Now we need to check. If we are applying a power supply to them. Okay, and power supply also we are applying like forward bias, reverse bias, that all stuff if we are applying to them, then we need to identify. Yes, someone has joined externally. Okay, so if we are applying any power supply to this 3 terminal, then what are the condition is going to be happen, that we need to discuss in this chapter or in this lecture. So depend upon that power supply you apply on this, both on this 3 terminal. Okay, and that is considered as a bias transistor type of the condition. So biasing, it means simply applying the external voltage to the source. Okay, if you are applying external voltage to the source, and according to that, whatever the condition it is going to be allowed, whether the current flow or rejecting the current flow or any other things, depend upon that, it is categorized under the 3 region, or it's categorized under the 3 condition. Okay, first, which is a cutoff, which is off condition, where transistor cannot work, or it is just off, so no current flow will be there. Saturation region we can say that's a fully on. Okay, an active region which is between cutoff and the saturation. Okay, so this is a 3 basically conditions are there under the cutoff, saturation, and active region. You can say in one state, you are making your transistor off, like you are giving a power supply to base, emitter, and collector in such a manner that transistor will not flow the current. Okay, it will not flow the current from emitter to collector. Like we can say, whatever the electron or whatever the current flow is starting from here, it is not go to the collector side. Or we can say it's not, this barrier is such type of the arrange, that barrier potential has been such type of the articulate, so current flow is not possible. So that we can say as a off condition. Saturation condition, we can say this is a fully on. Okay, you can say that transistor is fully on. It means full, whatever the current you have given, full amount of the current getting transfer from emitter to collector, you can say. While in the middle condition, it is controlled, which is an active region we have, which is between fully on and off. So that is region is an active region we have. And we need to learn that how this cutoff, saturation, and active region is going to be articulated. Okay. So these are the some of the conditions we have. Like if you are considering over here, you need to consider there are several stuff is going to be there. Like first, you can identify that which is your common terminal. Okay, before going to biasing any transistor, you need to first get an idea what is your common terminal. Okay, so in this diagram, I can say whatever the previous diagram I have seen. If I can say base is my common terminal, so I need to check the battery applied or power supply applied between emitter base junction and collector base junction. Okay, so before going to apply the biasing, first I need to set that what is my common junction is there, or what is my common terminal is there. So if I have make my terminal base as a common, so what is a power supply region is there between base and emitter and between collector and base. Okay, and depend upon the power supply you have given, it is either operate on cutoff, active, or saturation region. Okay, another stuff is also going to be there, like if you can make your emitter as a, let's take if you make your emitter as a common. So if you make your emitter as a common, then what are the power supply region? Emitter base and collector emitter. So that we can say base emitter junction, collector emitter junction. So that type of, depend upon the power supply you have applied between them, it going to be considered in either active or off saturation. If you are make your common as your common collector as your common terminal, then what are the junctions we have? Base collector, emitter collector. Okay, so depend upon that which terminal you are making common. According to that, there are different power supply terminal you can identify, and applying those power supply over there, forward or reverse, it is going to be considered under the, or it's going to be categorized under cutoff region, saturation region, or active region. Okay, so we are considering for as a first example as our base as a common. If we are applying power supply between base emitter junction and collector base junction, then there are three regions going to be applied, or it's going to be available. If you can make base emitter junction reverse bias as well as collector base junction reverse bias, then you can say you have a cutoff region. If you make both region reverse bias, and both region reverse bias and okay. Why? If you make base emitter junction bias and collector base junction reverse bias, so what will you make? Hello, sir.
Sorry, sir. Sorry. Sound is breaking.
Hello. Properly. Hello. Sound. Yes. Please give me a confirmation. Hello. Hello.
Not clear, sir. Not clear. Still.
So I have just reconnect. Just let me reconnect.
No, sir. No, sir.
Yes, is it coming okay? Hello?
Yes, sir. Okay, now.
Now it is okay. Let me just share my screen also. Screen is not visible. Is the screen visible? Yes, no?
Not yet, sir.
Not yet. Wait a second. I need to connect. Just a second. Still it is a blank screen. Play. Ooh. Yeah, is it available now? Okay.
Yes, sir.
Okay, now it is visible and audible properly. Okay. Yeah. Something a little bit on hold. Yeah. Where is our PPT? Yeah. So this is a stuff we have like the things that we have discussed in kind of the last lecture also, and that thing that I want to convey over here, that depend upon the biasing you have applied or depend upon the power supply you have applied, it is operating in a cutoff, active or saturation region. If that both terminal, base emitter junction and collector base junction, by considering that base is your common. So by considering base as your common, and if you apply both terminal, base emitter terminal and collector base terminal as a reverse bias, so it is a cutoff region. If you can say both region is going to be in forward, then it's going to be saturation region. While one region is forward, another region is reverse, then it's going to be an active region, you can say. Okay, so this type of the stuff is going to be possible to operate your transistor into the three way, like cutoff, active, or saturation. Okay, we will discuss a little bit more on that. I think this is a over here right now it's in confusing that what is reverse, forward, and all things. But we are going to discuss it whenever we are going with the common base circuit based diagram. Okay, so let me just go a little bit ahead over here. Okay, so this is a one example we have. I think you can see once that base is applied to the power supply. Over here we can say there is a common we can say there are emitter base and collector base transistor is there, NPN transistor is there, and in the NPN transistor, when your base will get the power supply connect through the switch, at that time all the current which is starting flow through this collector is going to be now started reaching at the emitter, and entire circuit is going to be completed over there. So you can say by having this diagram, you can say battery you have already applied. Okay, that current is already going to your to your collector, but it is not passing through this transistor. Why? Because your base is not allowing to do that. Once this base got the sufficient power supply, then and then only entire circuit is going to be complete and current flow will take place. Okay, so you can say like that the base terminal over here is become as a controlling terminal. Even if whenever you have not given a sufficient power supply to base, that transistor is not going to be on and complete circuit flow is not going to start it. Okay, so over here it is working the transistor as a switch. Whenever you apply the power supply at your base terminal, then and then your transistor is become the on. So this is a one type of the water flow type of the diagram I have explained over here. So if little bit amount of the current will came over here, which automatically make open the terminal for the collector and emitter, and that full flow of the current is going to be, or full flow of the water is going to be started. So this particular terminal or this red flag is depend on that what power supply you have given over here, or we can say what water supply you have given over here. Okay, so similar type of this stuff that we can consider as a transistor model. Well, it is depend on that whether transistor is on or off, working, not working, depend upon that what type of the power supply you have applied. Okay, One thing is simple over here, like you can say, one thing I can say, if I'm having this transistor, listen it very carefully, everyone. Okay, if I can say this is a NPN transistor. Why it is NPN? Because arrow is in this side. Okay, so the arrow, if arrow is going from base to emitter, then it is going to be NPN transistor. Okay, so we can say over here there are electrons are there. Over here there are electrons are there. Over here in between there are holes are there. Okay, so if current want to flow from here to there, this hole will not allowing to do that. Why? Because there are a depletion junction, there are a junction created between that. Now from external source, if external source you are applying a current on this terminal, if you are applying the external current on this terminal, then what happened? This hole is meet with the electron which is applied from the external, and it is become a neutral. Okay, we can say it's become the neutral. I can write. Sorry for the writing, but it's become a neutral. So if it is become a neutral, it means that whatever the depletion region between them, it's going to be reduced. Once it is going to be reduced, then current will start going to be flow. Okay, it is the same diagram as I have told you over here. By applying the current over here, it will make open a flag of this collector to emitter, and your regular current flow will be start. Now depend upon that what amount of the flow you are giving, according to that this collector and emitter is going to be open. Okay, and that we need to understand, like what is the condition and how much kind of the collector to emitter kind of the flow is going to be there. Okay, what are the conditions for that? All we need to discuss in this chapter. Okay, so there are two we can say current flow we can assume over here. If we can say the current, then we can say IE is summation of collector current plus base current. Amount of the current entering to base and amount of the current entering to collector, which is a summation, become as a IE. If you can say in the reverse direction flow of hole, then you can say amount of hole entering from emitter is equal to the distributed over base and the collector. But simply we can say IE equal to nothing but summation of IB plus IC. So this is a simple equation you need to keep in mind, that emitter current equal to base current plus collector current. This is a simple equation we have. Now over here there are a gain part we have. Okay, if we can take a ratio of IC by IE, how much current is giving from collector, how much is going to be available at emitter. If you're taking a ratio of both of them, then it's considered as a alpha. Simply, if you are taking another ratio, IC by IB, if you take the ratio of IC by IB, it becomes the beta. If you can take a ratio of IE by IB, okay, if you take a ratio of IE and IB, then it will become the gamma. Okay. Now, by looking to this alpha, beta, and gamma, can you tell me which gain value is going to be highest out of this? If you take a ratio of such current, IE, IC, IB, okay, can you tell me out of this alpha, beta, and gamma, which one is a larger, which one is a smaller? Ratio is smaller or ratio is larger? Are you getting my question or not? You need to open your mic and tell me, okay? Rather than typing in the chat box. Again, like, okay. Alpha is, Hana is saying that alpha is going to be small. True, true. Why? Because that IC and IE, which is little bit amount of the equal to both of them. Okay, so we can say IC equal to I, alpha is small, as well as IC by alpha, IE by IB, beta and gamma, IE by IB, IC by IB, which is going to be large. Okay, large we can say sometimes in thousands also, sometimes 100 also. So we can say the ratio of beta and gamma will be higher, while alpha is going to be smaller. Okay, that you can identify simply by looking to this diagram, that which one is higher, which one is lower. Yeah. So what is a transistor, that base curve and all the things we have? Okay, so that we need to understand over here. So base curve, how we can find out that what is a transistor characteristic, what is a base curve is going to be there. Okay, over here it is considered that, let me first go with this particular circuit, then I will again come back to the previous slide. Okay, over here you can understand. Can anybody tell me by opening the mic under which condition this transistor has connected? Which terminal is common over here? Tell me. Out of the emitter, base and collector, which terminal is common? Open your mic and tell me. Don't type in a chat box, my friend. Please. I need an answer in vocal. Quickly, my friend, by looking to this diagram, can you tell me which terminal is common between kind of these three? Hello. I'm not going to see in the chat box. Okay, you need to open your mic and tell me, please. Nobody has given the answer. I think not in any, everyone has not got the terminology over here. Let me explain you. Over here in this transistor, the common is going to be there. Over here, first you need to identify, like to look into the diagram, how you can identify. First of all, this is NPN transistor or PNP transistor. First question is there, what is the kind of the feature of the transistor, NPN or PNP? So if there is a NPN transistor, then what is a diagram for that? This is a transistor, this is a base, this is a condition, and always you can represent like that. Over here there is a collector, over here there is a emitter, and over here there is a base. You can simply write like this one: base, down emitter, above collector. You can write that. If arrow between base and emitter, see it carefully, arrow between base and emitter, if it is going to be like this one, base to emitter, then it is considered as a category of NPN transistor. Okay, similar type of the diagram, if you have written a similar type of the diagram and similar type of the notation, you have given collector, emitter and the base. If all the things are represent same as it is, but arrow is in reverse direction, see, now arrow is from emitter to base side, then it is considered as a PNP transistor. Okay, this is a simple identification is there. So now can anybody tell me by opening the mic, which transistor is it over here, NPN or PNP?
Hello, sir.
It's in.
Yes. Yes.
It's NPN, sir. NPN.
Yeah, it's an NPN transistor. Now NPN transistor, and you have find out that it's an NPN transistor and arrow is this side. So I can say this is my emitter, this is my base, and this is my collector. Is it okay? That terminal I have found out. Now see that out of these three terminal, which terminal is common? You can say this emitter is connected to the battery, so we can say that emitter is going to be a common terminal between base and collector. So I can say if this emitter is connected to ground, so it's a common emitter configuration. Okay. If base is going to be connected to ground, then common base terminal. If collector going to connect it to ground, then common collector terminal or common collector type of the condition. Okay, so right now it's a common emitter condition. So as I have explained you early, which junction is going to be formed? Like you have the transistor diagram like this one. You can say over here you are having a emitter, base and collector. and ammeter is connected to ground, then we can say which type of the junction is possible? Ammeter to base, ammeter to collector. So we can say base ammeter junction is going to be possible, as well as the another collector ammeter is going to be possible. Two condition. So that same thing is going to be applied over here. See, the battery has been connected between ammeter and base. Have you seen between this ammeter and base over here? As well as it is connected between collector and ammeter. It is ACB between the collector and ammeter. So we can say two type of the condition is possible, that power supply can be connected in possible base and ammeter, collector and ammeter. Is that understood by everyone? Yes or no? How we can identify the transistor terminal, type of transistor, and which terminal is open, then we can say whether it's a common ammeter, common base, or common collector configuration. We need to identify from that. Okay. Now we need to see that we need to apply a KVL over here in this loop. Okay. Kirchhoff's voltage law. So what you can say, if you apply a simple closed loop circuit, so we can say like its answer will be like minus VBB, okay, plus current is going to be passed through this one. I can say it is a base current. So if I can say it's a IB, it is IB. So I can say that transistor going to be, or the resistor is going to be drop IB RB as per the simple kind of the KVL rule, minus, I'm starting from this direction. So minus VBB plus RB IB plus, that is a drop over here, it's the VBE. And then it is reached to the end of this terminal. It is after this one. After this one, it is reached to the again. So we can say it is equal to 0. So this type of the equation possible, that I have written over here. And I'm making the now prime as a IB. If I make my IB as a prime, so what happened? It's going to be VBB minus VBE by IB, by RB. Okay. So we can say in the input side, in the input junction side, I can say over here in input side, if you want to identify the response of current which is flow through this base terminal, so it is depend upon that what is the power supply you have applied, amount of voltage drop on your base emitter junction, and the resistor that you have applied. If you know this three terminology, then you can find out what is the IB current. Okay. And now if I want to find out, and if I say that your gain, let me go with this, yes, if I say your beta, if I'll say now from this equation, I'll say your beta is going to be 100. If your beta is going to be 100, can you find out the other current, IE and IC? Yes or no? How you can find out? You can find out by using the equation of this one. So by putting IB in IE, you can say the condition like you can find out the gamma. Okay. As well as you have IB also, IE also. Okay. And if you have the, we can say that's a beta going to be also. So you can say you can find out the, by ratio taking IC and IB, you can find out the, from the beta, you can find out the IC. And by putting the value in this equation, you have IB, you have IC, you can find out IE also. And from that, you can find out the rest of the alpha and the gamma also. Okay. So by using this equation, IE, this alpha, beta, gamma, and by using this simple equation, you can find out rest of the current terminal, that what the possible current is going to be there. Is that understood? Yes or no? I need to go to check the chat box. So
Hello,
whatever
sir. Excuse
the
me.
question is there, I prefer. Yeah, please. Hey, tell me.
Sir, sir, I am
Yes, tell
just
me.
destinating at Marwari University right now. I'm in hostel, and I told you that asked me to extend
Okay.
the experiment 7 for me. It was not suitable for me to do this because of the travel. situation and process. So please, I request you to open the app. When I see it, it's closed already.
I'm not saying that canvas.
Yeah,
Hello,
assignment. I'm just for
assignment.
training purpose. I
Okay,
didn't
okay.
do assignment
What?
7.
Okay, wait. What? Wait. Hey, so you can say
Okay.
like in the next week we have the lab we have of 2 hours. Okay. So what you can do, like when we will meet on the lab, you just remind me that this is an assignment I have missed and I want to submit. So I will open it for you and then you can submit it. Okay. So such type of the relaxation we will give it to entrances to get if it is pending. Okay. So all the students, those who are traveling right now and coming to Marwadi, and if they have missed some of 1 or 2 session to submit because of the deadline, so they need to remind me during the laboratory session, that 2 hour laboratory session, and I will open for them. Is it okay? Yes or no? Hello, hey, okay. Did I say okay? Okay, Charlie, yeah. So Hannah has asked the question: why is the direction is the reverse in PNP from emitter to base? Now, why it is going to be happen? You tell me. Like if we have considered current flow by considering the electron, okay. So we can say in PNP majority carrier was the hole, okay. While in NPN majority carrier is going to be electron. So if we can consider electron as your current flow, so we can say obviously in PNP transistor that current flow direction will be reverse. And if you will consider hole as a major current flow, so we can say automatically electron is going to be reversed to them. That's why in NP and PNP, whatever the current direction you have, which is going to be altered in a other type of the transistor. This is the main reason. Okay. Hello. Repeat the formulas. Okay. Sir, can you show the KVL again? Repeat the formula. Okay, let me go to that formula. Yeah. So this is a KVL formula I have applied. Like it's a minus VBB. I'm taking the KVL formula over here. So what I'm taking minus VBB. This power supply voltage. Okay. And that I can say that I'm starting from minus terminal. So that's why minus VBB plus IBRB. Voltage drop across this resistor by using the IB as a current because it's a base terminal. That's why IB as a current and the resistor RB. So IBRB plus voltage drop across this base emitter junction and equal to 0. And if I make my IB as a prime, so what would be the answer? Answer will be like VBE minus VBE plus VBB divided by RB. Okay. And that's the simple equation like VBB minus VB divided by RB that I have written over here. VBB minus VB by RB. So if you have IB, and if I'll say you have a beta. If you have IB and if you have beta, so by putting this equation over here, you have beta, you have IB. Both you have. So can you find the IC out of that? Once you find the IC out of that, so you have IC, you have already IB, so you can find out the IE from that. And if you have find out IE, then by putting this IE on this equation, you can find out the alpha. And by putting IE over equation, you can find out the gamma. So that's the stuff I can say. Like if you are having a beta in one of the current, then by using that overall equation, this IE equation, this is I can say this IB equation, you can find out the rest of the terminal also. Is it okay? This formula, those who have the doubt? Okay. Yeah. Any doubt to anybody? Any doubt to anybody? Any question? No? Okay. Okay. So we have 15 minutes. Let me will go with the stuff. Let me clear this first of all. Screen. Yeah. So there are two kind of the, I can say characteristic is going to be possible. We can say there are input characteristic and the output characteristic. Okay, so input characteristic will tell you that amount of the base terminal, or we can say amount of the voltage you have applied on the base junction, base emitter junction. And where is our base emitter junction? Base emitter junction is over here. Okay, so if you are applying from the power supply base emitter junction, if it is going to more than 0.7, then we can say IB current is going to be start flowing drastically. We can say your input characteristic of the transistor is nothing but similar as a diode characteristic transistor, or we can say diode characteristic. Okay, in diode also the same type of the stuff. By increasing the voltage, if it is going to more than 0.7, then your current is going to start increasing. Similar to this stuff happening over here. If you are increasing the voltage over here, and after the 0.7, that your current is going to be start flowing from here to there. We can say that IB current is going to be start flowing in this route. Okay, so this is a equation is only and only depend, or that characteristic is only and only consider as, or we can say similar as a diode condition. Simple. But their output characteristic, it is going to be a little bit tricky. Output characteristic will be considered like this one. So how your IC current, whatever the IC current which is available over here, whatever the IC current available over here, and the value of VC which is depending upon this type of the relation. What is this type of the relation? You can say up to the some volt, that your current is start getting increased up to few milliampere. We can say that power supply you have given across this terminal, if you have increased that power supply in an initial condition up to this condition, so that condition your current is going to start increase at some level. After that, applying a sufficient amount of the voltage, it's become I can say constant up to some of the higher voltage. So by starting from, we can say from 0.4 or 0.5 to up to 40 volt, it is working as applying a fixed amount of the 10 microampere current. And after the very high current, a high voltage you have applied, it is going to be as a breakdown region. Okay, that your overall stuff is going to be break over here. And what happened, like there are three condition we have applied, or we have considered there are three stuff in our overall calculation, that active, saturation and cutoff. Okay, so where is the active region? Where there are a full amount of the flow, or we can say that controllable flow. Depend upon the voltage, it will give you kind of the fixed amount of the current. So this is a condition which is considered as the active region. After the breakdown region, your transistor is going to be damaged. Okay, so below this, like below this over here, like below to this terminal or below to this particular voltage, it is considered as a off state. This is going to be an off state. This is an active state. And whatever this region we have, okay, before reaching to any particular constant current, that state is considered as a saturation state. So these are the stuff is going to be happen whenever you can say, if you are applying, like similarly you can say, until and unless if you are not going to apply a sufficient amount of the voltage, then current is not going to be start flow. Once it is going to be flow, then it is flow up to some particular region until and unless that region getting breakdown. If you have applied so much high voltage, more than 40, then transistor get damaged and overall breakdown is going to be occur. Okay, so how this breakdown region occur, what are the stuff we have, that we need to understand deeply from the next lecture onwards. But you need to keep in mind that what are the conditions for that. Okay, or we can say what are the basic equations that we have studied. So let me just finish this stuff by applying a KCL in output loop. If I apply KVL or KCL in output loop over here, so what is the equation we have? Like it's a VCC. VCC, you can also say like that, VCE equal to VCC minus ICRC. Okay, you can make a prime of the other side also, and you can find out this equation. But this is a simple equation. VCE equal to VCC minus ICRC, and according to that, if you can find out IC current, then you can get the other current and other value also if you have the gain equation with you. If you can identify what is a power drop, so power drop is depend upon that how much current flow through that collector and how much power drop with voltage drop at the VCE junction. So if you are just making a multiplication of them, then you can find out the power drop in that particular system. Is it okay with everyone? So this is overall about the transistor and their different equation and all the things. We have 10 minutes of time, so everybody will please write the summary in the chat box. Then after you can write your enrollment number and then you can leave. If you have question, you can ask me. I am open for now for 10 minutes. So do it quickly because after the 10 minutes, I have also the another lecture in the Indian class. So please do it quickly, everyone. If you have any question, you can ask me right now, please. So Joseph, in session 8, how we can change the percentage? So by double clicking on that, it will give you the value, or there are some knob is there. If you change that online, if online this is a stop, so you can consider you make them 0 Faraday and you can make it full Faraday. Likewise, you can try it. If there is a variable capacitor is not there. Is it variable capacitor is available in online? Joseph, have you checked? So you can make it either making as a 0 Faraday or you can make it as a full. Likewise, you can check it. So, hey, what we can do, like you just remind me on the next laboratory that I have missed the session number 8. So you can, that I am going to allow you for resubmission. Yes, Udin, you have question you have not found in a diode in my offline multisim. Wait for a while, Udin, let me give you the, let me find out something for you. Wait for a while. Other student, if you don't have any query, any question, you just write your enrollment number and name, summary, and then you can leave. 10BQ015. Wait a second, Udin. Let me just check it from the canvas and I'm going to give you answer on that. Okay, wait for a while. So 10BQ, it's just a second. We're talking about session number 7, yeah. It is available in my circuit, but proper location, let me find it out.
Sir,
Yeah, please.
sir, it's in Schottky diode. Yes, sir.
Yes,
Yeah.
it's a 10BQ. Uh, Name is not written over here. That's why I'm. I think BQ. Hmm, Can you share your screen that and show that where is the actual location, because I have found it, but I have put it over here, but I have forgot where this is actual location is there. Hello. Yes, who is replying on about the Schottky diode? Can you tell me that where actually you have found from your system? So I will get the better idea from that.
Yes, sir. I found that on Schottky diode.
So can you share your screen and show us? I think because of the version might be there an issue. Can you
Okay,
show
sir.
that, Amiri? Yeah, share
Okay,
your
sir.
screen and show everyone.
Sir, is it visible?
Yes, it is visible. Yes.
I found it. Sir, here.
Okay, okay. Directly from that clipboard. Directly they are available.
Yes, sir. Here.
Schottky diode. I'm searching on the same stuff. I don't know why from my system it's not going to be came. Wait a minute, let me check. I think due to that, some of the issue like there are version variation is there. Might be there are a issue related to that, because I am also not having a 4-channel terminal oscilloscope in my system. So I think those who have like old multi-sim, new multi-sim, such type of the stuff is going to be there. So Udin, what you can do, take another Schottky diode and just connect, do your experiment. Don't worry. We will check with that also, that if there are another diode, then what happened. You can do it that also, Udin. It's not an issue. Okay. So I have the another lecture at 1, 2, 3. All of you guys, whatever the doubt and question, we will solve in the next lecture. Okay. You please write your enrollment number and leave. I'm just ending this session right now. Everyone, goodbye. Take care. Bye bye. Have a great weekend.